welcome to this energy seminar division of today. So I'm very happy today to introduce our speakers. First speaker is Josephine Wong. She's a graduate student from Stanford University, working with Roger Romani, I think. And they started a pre-doctoral fellowship here at CfA in July, just a few months ago. At the CfA, she's been studying stellar mass black holes and X-ray binaries, but specifically Cygnus X-3, about she's going to talk about today, with Mike McCollum and also Jack Steiner, using multi-wavelength spectral and polarization data like SMA, Chandra, and NICER. She's also interested in black holes more generally, everything from accretion disk physics to jet formation and relativity, both from the observational theoretical perspective. And today she's going to talk us about multi-wavelength studies of the flaring state of Cygnus X-3. With this, the floor is yours. And can you start?
Can you hear me okay? Not sure if the mic's on.
Maybe close it. Close it another thing. It's on. Yeah, we can.
It's on. It's on?
Just, yeah. Maybe try to talk with.
Talk to the mic. Okay. Hold it.
Yeah.
So hello everyone. Yeah, so as Federico said, I'm Josephine. I'm a pre-doctoral fellow here. And today I'm going to be talking about some of my work I've been doing here, studying Cygnus X-3 using multi-wavelength data. So just as an intro to start, Cygnus X-3 is a high-mass X-ray binary with a Wolf-Rayet companion star located about 10 kiloparsecs away with an orbital period of 4.8 hours. And there's several notable things about Cygnus X-3. It's a bright X-ray source, and it was actually one of the earliest discovered X-ray sources using sounding rockets in 1966. It is among all the X-ray binaries, the brightest in the radio, where during major flares it can reach up to 10 to 20 Janskys. It is also one of the few XRVs with detected gamma rays, meaning that it is a cosmic accelerator, accelerating particles up to relativistic energies. And also one of the few X-ray binaries with a Wolf-Rayet companion, which means that eventually we will hope that there will be gravitational waves produced when the Wolf-Rayet companion becomes a compact object and then they spiral inward. And that's extremely likely given the short orbital period, meaning the small orbital separation between the two, the companion and the compact object. So here's the image taken a composite of Chandra and SMA data, imaging data on the Cygnus X-3 region. So at the center, you have Cygnus X-3 in the X-rays, and then about 16 arc seconds away is another kind of X-ray, seemingly X-ray emitting source. And it turns out that that is actually a block globule, as they determined using CO measurements with the SMA. And it's called Cygnus X-3's little friend because it has apparently the same 4.8 hour modulation as Cygnus X-3, only phase shifted by about 0.6. And it acts as a mirror, reflecting off X-ray emission from Cygnus X-3. So this block globule is a stellar nursery, meaning that it's an area of where new stars can form. And we see evidence of that with the SMA. So we see these Doppler shifted protostellar jets shooting out from the block globule area. And so in this one picture, you kind of have basically kind of like a stellar cycle of life, where at Cygnus X-3 you have the compact stellar remnant with its main stellar companion. And next to it, a newborn star. So, it's kind of an interesting picture to see in all in one frame. So about a little bit more about the compact object itself. So Cygnus X-3 is located very close to the plane of the galaxy, between the Perseus arm and the outer arm. And so large optical extinction has precluded mass measurements of the compact object using normal measurement techniques like the radial velocity curves of the companion star. However, using other techniques, assuming certain properties of the Wolf-Rayet star, we've been able to obtain a mass measurement of 2.4 solar masses, which means that it's either a low mass X-ray, a low mass black hole, or a fairly massive neutron star. However, we have some other observational clues that can tell us or give us hints about what that compact object is. Specifically, it seems to show these spectral transitions that are reminiscent of black hole X-ray binaries. So that's kind of shown in this diagram here. So about 50% of the time, Cygnus X-3 is in this quiescent state, where you see low radio emission, about 100 to less than 100 millijanskees, and also low X-ray emission that's dominated by the hard X-ray components. As it moves into this transition region, we see the radio emissions start to increase, as well as the soft X-ray flux. And then following that, Cygnus X-3 can occupy a minor flaring state, where we see kind of these small bursts of radio emission, about 100 millijanskees, a couple hundred millijanskees. Eventually, right before a major flaring state, Cygnus X-3 go into this hypersoft state, where we see the radio emission suddenly plummet, as well as the hard X-ray. And that is, we believe, a sign that the jets in Cygnus X-3 is turning off. When Cygnus X-3 moves out of the hypersoft state back into, I guess, this less hypersoft state, we see a major flare erupt, where the radio emission can go up to 10 to 20 Janskees. And then, eventually Cygnus X-3 go back into the quiescent state. So these spectral states are very similar to those seen in other X-ray binaries. However, there are some notable differences. One of them is that we don't see the kind of traditional Q curve, where the X-ray binary first occupies an upper branch of higher luminosity, flares, and then drops in luminosity, and then returns to the quiescent state. Instead of that, it seems to linearly go between a quiescent and a hypersoft state. And moreover, in other X-ray binaries, we see the flare come when it transitions into the hypersoft state, but the reverse is true for Cygnus X-3. And I guess the current idea behind, our current explanation for that is due to the stellar wind around that's kind of embodying the system. And that's shown by this diagram here. So when Cygnus X-3 goes from a hard to soft state, it still has these radio jets. Remember that radio emission of less than 100 millijanskees. That radio jet is evacuating some area around the compact objects, so that we only see these minor flares erupt when Cygnus X-3 emits, goes into that minor flaring state. However, when it goes from the soft to hard, when it goes into that hypersoft state, the jet turns off completely. And so when Cygnus X-3 becomes active again, those jet-like emission features impacts the Wolf-Rayet stellar wind, and that is the cause of those really energetic flares that we see. So yeah, so we see jets and we actually can see these in radio images. So here is a VLA observation taken of the source about 3 months after a major flaring event. And we can see the progression. So between these is about 15 days per image. We can see the emergence of these bipolar jets coming out of the central region of Cygnus X-3. Here on the left image here is AMI data, so radio data taken at 15 gigahertz, where we see about several flares here. So these are major flaring events that we see here. And so they occur about like once or twice every year, once every 1 or 2 years. Okay, so now the observation that I've been looking at is a flaring state during the October and November 2021. And that's shown in these light curves here. So during that time, we had monitoring data from Fermi and the gamma rays, SWIFT and hard X-rays, MAXI and the soft X-rays, and radio data from AMI. And we also had nicer observations taken during this interval, delineated by the silver lines here, and as well as estimate observations in the red down here. So if you kind of look closely, you can see that the nicer observations took place right in the middle of this major flaring event, where there was 8 or so flares in X-rays separated by 3 or 4 days. And the idea is that we believe that those very closely separated in time flares created a hole through the stellar wind, allowing us to look at the emission from the inner region of the accretion disk. And that's very interesting because the emission from close to from the inner edges of the accretion disk, that gets affected by gravitational effects and Doppler boosting. Those spectral features reflect certain properties of the black hole, like its spin and inclination. And so by studying this, the spectrum of the nicer observation during this period, we can place constraints on the spin of the black hole, et cetera, which would be the first time we would be able to do this. So the technique we use is called line reflection spectroscopy, and this has been used to measure spins of several black hole X-ray binaries. The basic idea is that thermal emission from the accretion disk are compromised by the high energy electrons in the corona. Some of that coronal emission then gets reflected towards the disk and then bounce off. And so when that high energy emission from the corona hits the disk, that can eject an electron from the inner shell of certain species of elements listed down here. So once that electron gets kicked off, it's possible that another electron will occupy its place and emit a photon as a result. So those spectral features are called fluorescent K-alpha lines, and they're very prominent in the reflection spectrum. So this is a simulation that was done using just a simple power law for the incidence emission. And this down here is the reflection spectrum, where you can see all these narrow line features. Now, if the black hole has a non-zero spin, gravitational redshift and also Doppler effects will broaden and skew these intrinsically narrow lines, especially this prominent iron K-alpha line at 6.4 keV. The effect of that is kind of shown down here. So these are a couple other simulations done. Here's the variation of the effects on the K-alpha line with different inclination angles. So as you can see, with larger inclination, we're looking at the black hole more edge on, which means that we'll have a greater, more significant effects from these gravitational redshift and Doppler boosting. In addition, so this is if we vary spin, and so the effect that spin has is that as we increase the spin of the black hole, the radius of the innermost stable circular orbit decreases. And that is correlated to the inner edge of the accretion disk. So the radius of the innermost radius of the accretion disk shrinks, which means that these effects become much more prominent, and we see more broadening with increasing spin. Okay, so that's in a nutshell basically how line reflection spectroscopy works. Now I just want to provide some motivation behind this. So why are we interested in measuring the spin of black holes? So these are the number of measurements that we've taken of black hole X-ray binaries and AGN so far. So mainly, there are at least two things that we can learn from black hole spin. One of them is that we can learn about the formation history of the black hole. So this diagram here is a compilation of all of the AGN spins that have been measured as of 2019. And as we can see here, seems to be two populations of black hole AGN spins. Below 30 million solar masses, they tend to be pretty high, close to maximally spinning. And then above that, they tend to range between 0.4 and 0.7 in spin. And that is hinting that perhaps these really massive AGN are formed through incoherent, chaotic mergers that cause the aggregate spin to decrease. Whereas for these smaller population of AGN, perhaps they were created through accretion, coherent accretion. And so they were able to maintain their high spin values. Also, I will note that for some of these AGN, even the ones that have lower spin values, we have been able to see jets coming out of them, which is telling us that that spin is perhaps necessary, but not a sufficient condition for the production of these AGN jets. So in this chart here, these are all the spin measurements that we have of these stellar mass black hole X-ray binaries. And if we kind of glance through, you can see that they're all, well, not all, but most of them are pretty high. And compared to neutron stars and their natal spin measurements, these values are much higher, which kind of suggests that when neutron stars form, there's a significant effect due to magnetic braking that causes the spin to not be as high as for these black holes. So going back to looking at the nicer data, there's a package called RELSIL that is the state-of-the-art modeling tool for relativistic reflection spectrum, and has several advantages compared to its predecessors. Notably that it intrinsically includes the primary spectrum, which allows us to fold that into our model intrinsically. Also, it accounts for the angle dependence of the reflection. So when the photons are emitted at different angles, the relativistic broadening and all those effects play a role differently. And so the reflection spectrum does depend on angle, and RELSIL accounts for that. And it also has other features like it can fit for the different reflection fraction of, so the emission coming from the corona reflecting off the disk, it's able to account for different reflection fractions, as well as the disk density and the ionization. So the model that we've been using for our fitting is REL-CP, and these are the primary characteristics of that. It uses a parallel emissivity profile, so this is the coronal emissivity, as well as a Comptonized black body for the primary spectrum. and it's also able to fit for constant density and ionization in the disk. All right, so the thing about Cygnus X-3 that makes this much more challenging is that, as you can see here, it has many spectral features. So, there are emission lines, radiative recombination continua, which is when electron recombines with an ion emitting a photon that can occupy a continuous spectrum of energies. Absorption edges and lines, and also scattering and absorption from dust grains in the foreground spiral arms, aka the dust scattering halo. So we need to account for all these features in addition to the reflection spectrum itself in order to accurately model that reflection feature. However, once we do account for all of this, we can apply X-spec and do a spectral fit. And so when we do that, this is what we get. We get a chi-square value of, that's, well, relatively good, 1.28, using this algorithm. But the problem is that it seems like we're getting stuck in a local minimum. So this is if we run a test using X-spec. So we fix the spin value at each of these points here. So they're separated by 0.01 in spin. And as you can see, there's no one spin value that seems to be the best fit value. In fact, the chi-square value hardly changes at all as we vary spin. And similar thing for the inclination. And this is a sign that the algorithm that X-spec uses, which is this Levenberg-Marquardt algorithm, it's getting stuck in some local minimum that it can't emerge out of. And it kind of makes sense if we kind of look at how it works. It's a hybrid of gradient descent, meaning that you move in the direction of the direction that reduces your chi-square the fastest. And also this Gauss-Newton method, which assumes that your chi-square value is locally quadratic. And it uses this gradient descent method when your parameters are pretty far from optimal, and this Gauss-Newton method when it's close to being optimal. And so accounting for, if we think about how it works, we can understand why it's getting stuck in this local minimum. And so we need to turn to another technique. And it seemed after doing some research, it seems like one of the best solutions is nested sampling. So nested sampling is an MCMC method that's originally designed to calculate the evidence, but it's also equally powerful at calculating a posterior distribution for your parameters. And basically how it works is you start with a set of samples called live points distributed across your parameter space. And then the lowest likelihood sample is removed and replaced by one with higher likelihood. And so it iterates like this until the remaining volume is small enough that it negligibly contributes to your integral. So this method is much less susceptible to local minimum because you're looking at the parameter space as a whole, and it will traverse the entire parameter space. So as long as you have enough live points and enough points that you're sampling, you should be able to even constrain pretty complex distributions like the one shown here. And just as another example, this is using a nested sampler called Dynasty to recover this kind of egg box likelihood, which has pretty narrow multiple modes. So yeah, so for this reason, we turn to nested sampling. So here's kind of some like very preliminary results that I've gotten. And as you can see here, I'm not going to go into this too much detail. But as you can see, this is the spin parameter here, and we're getting a much tighter constraint. We're able to get a much tighter constraint on the value of it. And I will note that some of the other values, such as the NH here and the inclination of the disk, are also consistent with values that have been measured in the literature. So it seems like a promising avenue that we're currently exploring, but we need to do a little bit more testing. And also the posterior needs to be sampled much more. Okay, so I just want to talk about two more things that we're kind of exploring with the data. One of them is QPOs. So for Cygnus X-3, we don't have any measurements of these typical type A to C QPOs, but we have seen millihertz QPOs after major flaring events. So these are just a couple other couple of examples. Exosat saw 0.7 to 15 millihertz QPOs for 5 to 40 cycles. In 1991, we saw an 8 millihertz QPO in 20 to 100 keV. But then when we looked at RxTE data from 1996 to 2000, we didn't see any QPOs. So this is a sign that these are pretty sporadic and probably time sensitive and short-lived. So looking at, so I didn't mention this, but 2019, there's another flaring state where we also see evidence of this relativistic iron line. So we're including that in our data analysis as well. So in the 2019 NICER data observation, we see potential evidence for another sign of millihertz QPOs. So here is a fit. So this is the, I guess, power spectrum for that data set. And we've done a parallel fit to that power spectrum, which gives us an index of about 2, consistent with literature values. And then we do basically like an MCMC run simulating this model spectrum for a number of times. And then we calculate the different confidence intervals. So the 95th all the way up to 99.5 percentile. And we do see some features in the power spectrum that are above that confidence level. So one at 3.8, 7.6, which are interesting harmonics of each other, as well as one at 8.6 millihertz. So this is interesting. We'll need to explore this a little bit more and try to see this in the actual light curve to be completely sure. But this seems to be suggesting that there are these millihertz QPOs. And then finally, I'll just mention the SMA polarization, which I have not gotten a chance to look at too deeply yet. But based on this very preliminary look done by my advisor, Mike, it seems like during that November 2021 flare, in the radio, there seems to be a polarized flare without a unpolarized component counterpart, as well as a rapid swing in the polarization angle here of about like 60 degrees. That's kind of reminiscent of polarization swings in blazars. So we're going to be exploring that a little bit more in the future. So yeah, so I just want to wrap up there and take questions.
Thank you. Really fascinating. Thanks, Josephine. Do we have any question? Let's say a couple of questions.
Thanks for the very interesting talk. You mentioned in the line reflection spectroscopy that both increasing inclination from hole and increasing spin bottom line. So how would you kind of work that degeneracy when you try to fit all the spectroscopy?
Yeah, so the inclination and the spin affects the broadening, affect the line in different ways. The inclination tends to broaden the line in both on the red side and the blue side, because we see, for example, if we're looking at the disk edge on, right, we're going to see symmetrically effects from, red shift and blue shift. So it's going to affect both edges of your line. Whereas for the spin, it's going to primarily affect the blue end based on simulations. So they have different effects on the spectrum. And that's probably one way to break that degeneracy.
Yeah, thank you. And really nice talk and the intriguing connection with lasers.
So I wonder, just a quick observational question, is there any attempt to spatially resolve the polarization, like see where these like polarization swings that happen, or it's on very small angular scales?
Okay, that's interesting. I think with the VLA, we do have the angular resolution to be able to resolve the jets. I'm just wondering, like, statistics wise, if there would be enough counts to really significantly measure the polarization if we, for example, divide it up into different, different regions. But that's maybe something we could explore. Yeah, maybe Mike has something.
Yeah, I mean, I can just say that we actually, there is VLBI for Cyg X-3. It extends out to about 120 milliarcseconds. And so, yeah, you can see the structure. We actually have accepted for the next major flare a VLBA proposal, which we're going to do. What? Triggering proposal, yes. It's a triggering proposal. It's good for about the current cycle, the next 2 semesters. And so we're going to do, we have 30 VLBA hours, 5 days, 6 hours each, where we're going to actually watch the jet as it merges out and try to get daily cadence if possible with the VLBA. We'll be doing 15 and 22 gigahertz and giving polarization on that. Yeah.
Great, thank you. Let's thanks Josephine again. Let me introduce our second speaker of the day. And also trying to. Do you want to do it? You want to?
Oh, yeah, sure, I got it.
Thank you. So our second speaker of today is Tom Wagg. He's a 4th year and final year PhD student at the University of Washington, broadly interested in massive binary evolution and population synthesis, and he's also excited by the potential constraints offered by the positions and kinematic of sources. Over the course of the PhD, he's worked also on LISA gravitational wave predictions, near-Earth objects forecasting for LSST, and astroseismology of accretor stars. Oh, okay, so today he's going to talk us about integrated binary evolution and galactic dynamics with Cogsworth. Thank you. The floor is yours.
Thank you very much. Just do something like that. Splendid. Set a timer going so I don't take all of your time and say hello. I'm Tom. I'm as I said, 4th year grad student at University of Washington. Today I'm going to be talking to you about a project I'm quite excited about, where I'm integrating binary evolution and population synthesis with galactic dynamics so that we can kind of look at the positions and kinematics of all different types of sources and do things like this. And this is in collaboration with a bunch of wonderful people that I am very grateful to. So I like binary stars, and if you ask anyone who likes binary stars about them, the first thing they will tell you is that the majority of massive stars are in interacting binary systems. Over 70% of O stars are going to exchange mass with a companion at some point in their lifetime. And what this means is that only about 30% of these are effectively single. The rest will have some sort of stripping or accretion or merger, which are going to significantly affect their evolution. And these massive stars are important. They play a critical role in all sorts of things, particularly in terms of galaxy evolution. If you want to what you need to be accounting for are stellar winds and supernova feedback for the kinds of regulation of star formation that's going on in galaxies. And if you want to reproduce the observed galactic population, you really need to be doing these sorts of things to get everything properly done correctly. And it's also important for how many transient events you're going to make, how many X-ray binaries are you going to make in terms of all your binary evolution. Understanding a lot of these uncertain parameters is important. Problem is, a lot of them are very uncertain. This binary evolution is important, but there are things that we aren't quite sure about. A lot of these parameters poorly constrained over several orders of magnitude. We think about common envelope evolution, where you've got unstable mass transfer between 2 stars. They have this kind of common envelope. They're trying to work out, what fraction of the orbital energy is going to be available to unbind this envelope. It's this alpha parameter. It's very much kind of a fudge parameter in many ways. We don't know whether this is 0.1 or whether it's 10, and it's very uncertain in that way. Similarly, you're looking at supernova natal kicks and how strong are these kicks? Are they bimodal? It's something that's very uncertain. And so we want to understand this better. And one way that we could do this is by thinking about the positions and kinematics of all sorts of binary massive stars. Because if you think about a single massive star, there might not be that much information there. They're going to live fast, they're going to die young, and they're going to die very close to where they're born. The same story is not true for binary stars. In this case, they can acquire high velocities. If we start with 2 stars up here, One of them slightly more massive than the other one. This one's going to reach core collapse. Let's say it becomes some black hole with a natal kick, and it flies off with that velocity. The secondary star is also at this, say it's disrupted. The secondary star is going to fly off with pretty much whatever its pre-supernova orbital velocity was. And that encodes a lot of information about how the kind of orbit of the system changed over time, things like mass transfer, common envelopes, all that sort of stuff. And so if we look at stars and remnants at large separations, or with reduced spatial correlations, there's a lot of information there to learn about binaries. What we need for this is the theoretical infrastructure to actually model it. And that's where Cogsworth comes in. And so this is a new code that I have released that kind of puts population synthesis and galactic dynamics together so that we can properly make predictions for these positions kinematics. Brief note on the name, it's not an acronym, I just thought it was fun to say. It's just, it sounds sort of like a butler, it's sort of English. But what this does is puts together kind of two main components, which is population synthesis with Katie Brevik's cosmic code. This does all of your, given some initial binary, how does it evolve, what's its end state, that's all included in that case. And then what we do is put it together with galactic dynamics through Adrian Presswheelan's Gala code. And what this allows you to do is take all of your systems, evolve them, but place them in a galaxy and integrate them forward and start to say where have they ended up, and when they're transferring mass onto a compact object, where are they in the galaxy, things like that. So to give you an example, if we look at the galactic orbit of a disrupting binary, I'm just going to show you one binary in 3 different projections moving across the galaxy. And what you can see is this is just something evolved in a Milky Way potential. It kind of starts evolving here, and then it splits at this point. That's the first supernova occurs. And then you have 2 stars. It tracks both of them. You can kind of see it better in this projection, but after the split there, then here you can see a second supernova move the other star as well. And so at any point in this plot, I can tell you what are the masses of the 2 stars, what were their orbital periods before they were disrupted, things like that. And so that's like the very basic overview, but it's also very flexible. So if you know anything about population synthesis, you should not trust one population synthesis model, you should do lots of variations. And so what this allows you to do is change all of those binary physics assumptions. What is that alpha common envelope? What is the supernova natal kick? And many other things, like 40 different settings. You can also change your initial binary sampling. What do you want to use for your initial mass function, your orbital period distribution, all that sort of thing. And you can change the galaxy aspect as well. So what star formation history do you want to use? You can use a very simple starburst and just say it's just in this location, or you can have something as complex as a multi-component Milky Way model that has a high alpha disk, a low alpha disk, a bulge, etc. In addition, you can change the galactic potential. So any potential you can define in Gala, you can also do it in Cogsworth. So this lets you do a Milky Way, it lets you do also a dwarf galaxy, and you can evolve these similar ways. And maybe you don't care about how to define specific star formation histories and galactic potentials. The nice thing is you don't have to. You can also use a fire or a Changa hydrodynamical simulation as initial conditions to these simulations. So this is useful because, these have proper initial spatial correlations. We know that stars don't form by themselves, they form in clusters. And so if we want to, make predictions for the final positions and kinematics of binaries, we better get the initial spatial correlations a bit better as well. So that's where this is useful. So just to give you an example of what this might look like, I'm going to show you just one cluster that I've just plucked out of a fire simulation, M11H if you care. And what I'm going to show you is as a function of galactocentric radius and galactocentric height, how the cluster evolves. It's going to start off down here in the bottom left, and you can see it evolve upwards towards the top right over time. So the cluster is, not a bound cluster, it's going to disperse over time through some initial velocity dispersion. You can see the graded lines in the background are what I would call the more boring stars, but the lower mass stars that aren't experiencing supernova. These are just moving along, dispersing over time. But the fun ones are the colorful ones. These have some sort of supernova go off. So just to talk you through some of them, say we look at this dark blue one here, you can see there are 2 supernova in quick succession from the primary and the secondary. But in both cases, the binary remains bound and then gets ejected out of the cluster after the second. Let's look at the light blue one next here. You can see that it goes along. There's a later primary supernova, which sends a compact object this way, and a star that way, and then the star also goes supernova. Both things are ejected from the cluster, but in different directions. And you can even see in the green example that as it goes along here, there is a supernova later on, but it's weak enough that the natal kick isn't particularly strong, the binary remains bound, and the binary remains bound to the cluster. And you can see it follows the pattern, afterwards. And so we can track all of these kind of diverse outcomes through Cogsworth in a single simple simulation. And so those are all the inputs. what do you get at? Well, you get the rates and distributions of your intrinsic population, all the usual things you'd get through PopSynth. But now what we give you as well is the kinematics of all of your massive stars and compact objects. And this can be very useful for thinking about binary evolution. So to give you an example, now I'm showing you the exact same initial binary population evolved in 4 different ways, where in the top half, it's in a Milky Way disk, and in the bottom half, it's in the Carina dwarf galaxy. And then from left to right, what I'm doing is varying alpha common envelope from 1 to 0.1. And so what this means is less of the orbital energy is available for ejecting this envelope. And so more things end up merging during a common envelope. And so you have fewer systems where the secondary star is ejected from a binary. And so now, if we look at the present day spatial locations, I should have told you what's in the density distributions of all of your massive stars. These are just contours up to your 95th percentile, and then the dots are just the final 5%. You can see that the spatial distribution, specifically the scale height of your distribution, is significantly altered just by changing one parameter in the binary evolution. You can see many fewer things are reaching high scale heights, and this is true in both galaxies. And so there's lots of information in there. Though there are different parameters that could do this, there are degeneracies. The nice thing is we can look at different populations at the same time. You don't need to just look at your runaway stars, you can also look at your X-ray binaries and also look at where gravitational wave sources are or short gamma ray bursts. And a lot of these have different dependencies and can break some of those degeneracies. And then final thing that comes out of it, you've got all of your intrinsic distributions. You can then also turn them into observables. So what we have are prescriptions for disk maps, prescriptions for bolometric corrections using the MIST isochrones and the Gaia empirical selection function. So you can run one single Cogsworth simulation and then ask, please give me the subset of this population that's observed in Gaia, and it will just do it for you. So very useful for actually comparing to observations. And I will show you one slide that has code on it, and this is the only slide I promise. But I want to demonstrate to you that it's easy to use. Because if you want to make a simulation, you just say, right, I want to use Cogsworth, I want to start a population, I'll have 1,000 binaries on 8 cores, I'm going to use this model for the star formation history, this galactic potential, and I'm going to change alpha common envelope to 0.5. And then if you want to evolve it, then you're just like, okay, great, sample the binaries, sample the galaxy, do your evolution. You can then get out a table of your evolution, you can get your orbits for all of your systems. You can even say, give me the observables in these specific filters, give me the binary numbers that are observed. And at the very end, depending on what you have done, it will then, you can say, give me my citations, and it will choose the specific papers that you have relied upon and give you a LaTeX and a BibTeX citation to put into your paper. And so there's lots of documentation. It's all available here on this link. It's on all the slides. I have lots of tutorials that go through in kind of a interactive manner. And lots of examples as well, just for like quick plots if you want to make it. So I encourage you to try it out for whatever sources you might be interested in. But enough code for one slide. I will now tell you about some actual applications that we have been using Cogsworth. So first, before I talk about things I'm doing, I want to tell you about some stuff that I've got some students working on because they're doing some really interesting work. So first, Sam and Vita is doing some very cool stuff thinking about the offset of short gamma ray bursts from their host galaxies. So this is the thought is that you've got a binary neutron star that has been ejected by its kicks from the galaxy, merged, and then had a short gamma ray burst, which are observed often far from their host galaxies, often completely hostless. And we can make predictions for this using Cogsworth. In particular, the thing that we're going to do different, or that we are doing differently right now from previous work, is accounting for a properly time-evolving potential. Most previous works assume a static gravitational potential for all of their galaxies. But this isn't quite how it works. Often these things can be formed, long ago, where the galaxy is not quite as big as it is. It has a very different potential. Might be easier to escape, and this can change a lot of those distributions. So that's something that Simon Vita is working on right now. Frank is looking at some LISA sources. So I have shown in previous work that we'll find lots of massive double compact objects in LISA, in addition to double white dwarfs that everyone's excited about with LISA. Problem is, it can be hard to distinguish them based on their chirp mass alone. Because the mass of a double neutron star versus a double white dwarf is reasonably similar. If your errors are fairly large, it's hard to tell the difference. So what Frank is doing is using Cogsworth, in addition to legwork, which is a different code I've done in the past, to think about whether we can use the sky locations and the eccentricity as well to distinguish these sources. Because you'd expect that these kicked sources that have black holes or neutron stars in them might be outside of the plane, have some eccentricity, and this can be used as an additional way to kind of differentiate between these two populations. And that's where LISA is nice, where you can actually measure eccentricity, unlike LIGO, where they are often circular before you get there. And then finally, Hannah and Kevin, who you can see are a little more shy and don't want to share their photos, are looking at how binary interactions can kind of change the galactic underworld, as it was coined by this paper, which is just the spatial distribution of black holes and neutron stars in the Milky Way. But what they did in this paper is assume single star evolution. And what Kevin and Hannah are investigating is, could binary interactions change this? If you have two kicks, could you end up getting things further away? You also have merger products that can produce more compact objects than you might see otherwise. And so that's something that they're looking into. And I'll talk about things that I'm actually doing. So one thing to consider is that the timing and location of supernova feedback is going to impact its efficiency. Just to give you an example, let's say we have a star that's formed in that cloud there. And let's assume this star is a single star. So it lives there, dies there, and explodes there. And that's where you get your feedback, within your natal cloud. But let's take this star. This one, let's say it was formed in a binary. Its primary is exploded, and then it gets ejected over here, then explodes. That's going to have a very different effect on the galaxy. It's going to change your feedback in that you're going to have less feedback within your cloud, and you're also going to have feedback in diffuse and lower density regions within the galaxy. And this is interesting to look at, because if you ask any hydrosim person what they do for their subgrid model, the assumption is always single star evolution. Any fire or China simulation are all assuming binaries aren't existing for this sort of feedback. The assumption for their kind of type 2 core collapse supernova feedback prescription is that it ends after 37 million years-ish. And it's just a two-step function exactly like that. But, previous papers before I've even looked at this have shown that binary evolution can get you supernova happening even up to 200 million years, and that supernova from binary stars can be significantly displaced from their birth cluster. And so what we wanted to do was basically use Cogsworth to investigate this and see how it might change galaxy evolution. And there are previous papers that's looked at this. So some people have looked at this and said runaway stars could have a strong effect, others say it's weaker, but they basically assume that stars get some kicks and then see what happens, whereas we can now actually say this. But the main impacts are on the star formation rate and the energy loading factors. And in particular, it has been shown that if you have enough supernovae in low density environments, you can fully dictate a lot of the galactic outflow rates. So it can be very important for how many of these things are properly escaping their clusters or the natal clouds they're born in. So what we did was a Cogsworth simulation based on the Fire M11H simulation, which is just a dwarf-like galaxy with a dwarf galaxy with a disk in it. What we did is take every star particle that formed in the last 150 million years. In a fire simulation, star particles are about 10,000 solar masses. They don't, fully resolve stars. And so we take those star particles, we draw binary populations that match the total masses of the particles. That gives you about 2.5 million binaries. We then evolve them through present day, through the galactic potential, which we have fit using basis functions to the actual galactic mass distribution in the fire simulation. And then what we see is I'm going to show you just like a kind of picture of the galaxy at present day, based on an edge on. And you can see pretty disk-like, but it also has some nice spiral arms. We can see there are regions where there hasn't been any recent star formation. And I've tricked you, because this is the version that is just single star evolution. But if I actually account for the binaries, the picture looks a little different. If I switch between them now, you can see that binaries can actually put your stars in very strange locations. You can get things much further out, and in particular, you can fill in regions where there wasn't any recent star formation. So these are the low density environments that you might not expect to have feedback in if you just assume single star evolution. So first, let's look at the time. So this is showing you, as a function of time, how does the supernova rate change? And it's going to be a stacked histogram with some different colors. The dark blue ones are your primary stars, the initially more massive star in a binary. Secondaries are the initially less massive star. There's light blue ones, there's not many of these, but these are the effectively single ones, the ones that were so wide they had no interaction. And then purple are the fun ones, where they are two stars that have merged as stars, then got supernova. And they're going to be important in this plot. So distribution looks like this. You can see that over time, I should say dashed lines here are showing you for the Fire 2 and Fire 3 simulations what they assume as the cutoff for your supernova feedback. And you can see that aligns pretty nicely with the blue and the green. Your primary and your secondary stars within your binaries. There are some small tails out where you've had enough mass transfer to significantly change your nuclear timescale. But clearly the important thing here are the purple ones. So these are your merger products. So these are two stars that have merged and then gone supernova. And so if you want to get a supernova to occur later on, what you need are two lower mass stars, which take longer to evolve, may not have reached core collapse by themselves, but together, once they're finished evolving, merge, once one reaches the end of its main sequence and expands and has unstable mass transfer, and then you can end up getting supernova here, or even really out far to 200 million years for the end of the tail. So this gives you late feedback within your galaxy. That's the time. We also looked at the distances. So this is now showing you how the location varies relative to its parent cluster. So what is the location of the cluster? The location of this, location of the cluster at the time of the supernova, distance between the two. That's what this distribution is. The assumption in these simulations is that the distance is 0. You can see this is a log scale. The distance is not 0. The distribution looks like this. And so for the purposes of how the feedback is changing, within 100 parsecs of the parent cluster, it's not that important. We don't have to worry too much about this part of the distribution. That's going to act very similarly to the rest of the feedback. But the interesting part is this tail out here, which you can see doesn't really include primary stars. They are all more to the left because they act a lot like single stars. You see merger products ending up further away. That's just because they live longer, so have longer to disperse from the cluster. The green ones are the fun ones though. So these are your secondary stars, where you've had a primary star explode, the secondary star has been ejected with whatever its orbital velocity was, and ended up very far from the parent cluster, in some cases several kiloparsecs. And so this can give you feedback in weird places, often out of the plane, in low density regimes, and kind of change these curves. And I said to you at the start, never trust just one population synthesis model. And so what we did was lots of them. And so that's just our fiducial model. I'm going to show you variations across common envelope, mass transfer, supernova kit physics. You can see the specifics down here. And just for the overall interquartile range of the distribution, it looks like this. You can see it's pretty robust. There's actually very little variation across here. The primary stars in particular change very little. The secondary stars show the biggest variation, so the very tails of your distribution are slightly sensitive to the stability of mass transfer and its efficiency as well. But the merger products as well show very little variation. And so this is kind of annoying for me because there's not much information about binary physics in it. But for galaxy evolution and putting these prescriptions into hydrosims going forwards, this is quite useful because the results are fairly robust to lots of variations in binary physics. And I'll show you one slide just before I finish, just to say I'm around until Friday, so I can talk about lots of different things. If you want to talk about gravitational waves and LISA sources, I've made predictions for that in the past, and I've made a code for calculating signal-to-noise ratios. So if you have sources that you want to know if they're detectable, we can do that. I've also worked on astroseismology, thinking about how mass transfer changes the astroseismic signal of a star. So a star that accretes mass actually has different astroseismic signals for the rest of its main sequence after this. We show for a slowly pulsating B star anyway. I've also been thinking about runaway stars recently and how we identify them, because the definitions for an observer versus a theorist aren't quite compatible. And so when we've been using runaway stars to think about binary evolution, there are some problems in that it's not entirely the same population. So I have some ideas for how we could make that better. And then one last random thing is that I made something called the Software Citation Station recently, which is a website where you can basically go, click on all the software that you've used, get the specific versions based on what's available on Zenodo, and then it will just automatically give you something to put into your manuscript, bib tech to go with it, and then you can cite your software properly and give everyone the nice credit they are due, and you don't have to go through all the stress of finding it on each website. So with that, I will say, here are my takeaways. Thank you for listening, and I'd love some questions.
Thank you so much. That will stay in time. So, do we have questions? Good.
Wondering if you could calculate, I'm sure you could, the fraction of supernovae that go off in pre-existing bubbles.
Yes, absolutely. So I've been talking with Uli Steinbandel about this recently, about are they going on in super bubbles that are already there, and how would this change the outflow rates? Yes, definitely something we're thinking about.
Nice talk.
Thank you.
You did mention triple companions, which in our classic paper pieces here, Maximo and then Stefano, which I'm sure you know all about. Half of those binaries have triple companions. Oftentimes even more than that. So what do you do with those in this scenario?
Yes, absolutely. Definitely something we should be considering, and something that we're not currently. So triples aren't included in here, but in principle, what this does is connect an existing population in this code to galactic dynamics, but there's nothing about it that really says this needs to be cosmic on the inside. So there are triple codes out there like MSE, TSE, TRES, that we could in principle could connect to and then properly make predictions for triples as well, which, as you say, are very numerous and we should be thinking about.
Any more questions? You send it online? No? Let's give another 10 seconds. What we-
So I'm interested in the fraction, this amazing plot that you made of like the fraction of supernovae that are coming from sort of different like portions of the population. And so I'm even just thinking about observations of supernovae, and something we often have is like some estimate of the stellar population age in that vicinity. Do you think that's enough to start to learn about like, are supernovae different if they come from these merger products or that, or do you need to be really granular like to the cluster? Like, is this something we can do in the local group or?
I think it could be interesting. I think there's a lot of information in like spatial correlations of supernova with their like kind of what's going on in the nearby region. So I think there's interesting stuff with like strip supernovae versus accretor supernovae as well, which I think could be there as well. But also, you know, the mergers, it's nice because the things that are far away from their cluster, if you can also get the time, if you can imagine what I have a plot of the 2D distribution, but I don't have it here right now. But the things that are far away, if it's early, then it's the secondaries, and if it's late, then it's the merger products. And so you can actually do something timing wise as well, which I think could be interesting to look at.
Cool.
All right. For the sake of time, maybe let's close here, but as Tom said, it's going to be clear for the rest of the week, and then Josephine is here until December for a few more months, so you have plenty of time if you want to chat with both of them. So thank you, and see you next week.